Good afternoon. I am still on jury duty. Actually, right now it's Saturday, and I'm spending my Saturday recording lessons for you. But it's okay. That's part of what I signed on for. Today we're going to look at section 3.1 on the derivative of a function. Just as a quick reminder, tomorrow in class you will have a quiz on sections 2.1 and 2.3. So 2.1 through 2.3. Please be sure that you're ready for that. We will take that quiz whether I am there or not. I'm anticipating not being there. So, all right, the derivative of a function. This is one of the two big ideas of calculus. If the slope of a curve, y equals f of x, exists at x equals a, and remember that's the limit as h goes to 0 of f of a plus h minus f of a over h, if that exists, then this limit is called the derivative of f at a. So there are several different ways we can write that. We could write that this way as well. The derivative of a function f with respect to the variable x is the function f. And notice there's a little, it's not an apostrophe because it's straight. It's a red prime, f prime of x, whose value at x is given by the limit as h approaches 0 of f of x plus h minus f of x over h, provided that that limit exists. If this limit exists, we say at a point A, we say that f is differentiable at x equals a. And you're like, where did differentiable come from? I thought it was derivative. Why isn't it derivatable? Well, derivatable sounds weird to start with. But the other reason is, and more importantly, this comes from the difference quotient. So that's why it ends up being differentiable. So let's find the derivative of f of x equals x cubed. Okay, you may have already learned this rule in your AP Physics class. We're going to show why this works. So f prime of x is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. In this case, that will be the limit, and you got to keep writing that limit until you have evaluated it as h goes to 0 of, I'm going to replace x with x plus h. So that's going to be x plus h quantity cubed minus f of x is x cubed all over h. Now we've got to cube x plus h. Hopefully at some point, either in Algebra 2 or in pre-cal, you learned a quick way to do that with the coefficients. You may have learned the Pascal's triangle, where that's 1, 1, this is 1, these two added together is 2, and that's 1, and this is 1, this will be 3 because 1 plus 2 is 3, this is 3, this is 1. This is for squaring, this is for cubing. If it was to the 4th power, you would go on. It gives you the coefficients. If not, you can do that by hand, but that's super easy. So the limit as h goes to 0. This is going to be x cubed plus this coefficient 3 times x squared times h plus, now I'm to the next one, 3 times x times h squared, and then plus 1h cubed minus the x cubed that was there, all over h. So that'll be equal to the limit as h goes to 0. Notice in the numerator I have a positive x cubed and a negative x cubed, so those drop out. So I've got 3x squared h plus 3xh squared plus h cubed all over h. Notice every term in the numerator has h as a factor, so I can go ahead and perform the division that's implied in that fraction. So this will be the limit as h goes to 0 of 3x squared h divided by h is just 3x squared plus 3xh squared divided by h is 3xh plus h cubed divided by h is h squared. Take the limit as h goes to 0. If h goes to 0, the 3x squared is unaffected. 3x times something going to 0 goes to 0. Something going to 0 squared is 0. So we end up with f prime of x is 3x squared. And again, you may have learned in physics how to get from this to this. For now, you will not be allowed to use that rule in this class until we actually get to it and show why the heck it works. So there's an alternative definition, especially if you're trying to find the derivative at a particular point, x equals a. We can do it this way. F prime at a is the limit as x approaches a of f of x minus f of a over x minus a. And that harkens back to the idea that we want, two different points on the curve getting really close together when x gets really close to the value a. So just real quickly, you don't have to draw this. If this is a, then this would be f of a. And then x is just some point over here. So what's going to happen is we're moving this x point along this direction so that this point is moving this way. And then this is just the slope of the line connecting those 2 points. As we move this direction, what does that slope get closer and closer to? So again, this is just an alternate definition. Occasionally, it's easier to use this. If you want to, you can. Your book sometimes will instruct you to use the alternate form. So let's take a look at an example of that. Use the alternate derivative to find, let's not find f prime of x. Let's do f prime at 4. So f prime at 4 is going to be the limit as x approaches 4 of, let's go back up to that real quick. Let's say, what was that? F of x minus f of a. Okay. So f of x is the square root of x minus f at a, be the square root of 4, all over x minus a. That's going to be x minus 4. And we've got a real problem here in that how in the world are we going to simplify this? Because if I substitute in 4 now, I get 0 in the numerator and 0 in the denominator. That's always going to happen when we're doing a derivative problem. The key is, first of all, not to take the square root of 4 and get 2. Although you can do that, it kind of clouds the issue. The key is to multiply by what's called the conjugate of the square root of x minus the square root of 4. You did some conjugates in pre-cal. If you were an honors pre-cal, you had to do this. That would be the square root of x plus the square root of 4 over the square root of x plus the square root of 4. We're going to multiply by a fancy form of 1. How is that going to be helpful to us? Well, let's see. I'm going to have the limit as x approaches 4 of the square root of x times the square root of x is x. And then for my middle term, I'm going to have the square root of x times the square root of 4 is the square root of 4x. And then I'm going to have minus the square root of 4 times the square root of x will be the square root of 4x also. So I'm going to end up with 0. I'm going to go ahead and write it this time, but I don't normally. So I'm going to have plus the square root of 4x minus the square root of 4x. Those are going to drop out. And then I have minus the square root of 4 times positive square root of 4. So that's going to be minus 4 all over x minus 4. X minus 4 times the square root of x minus the square root of 4. Plus, excuse me. And you may wonder, well, why don't I distribute on bottom? I don't distribute on bottom because of something that's going to happen at this point. You really are kind of looking ahead on a problem like this. So then f prime at 4. In the numerator, I have x minus 4, and I'm going to put it in parentheses so that it's more obvious what I'm about to do. Oh, hey, look, in the denominator, I have x minus 4 as a factor also. And I did a bad thing by not writing the limit, so I'm going to have to squeeze it in there. And notice that we don't care what happens at 4, so the fact that I'm canceling 0 over 0 out is just fine. So this is going to be the limit as x approaches 4 of 1, it's not 0, it's 1, of the square root of x plus the square root of 4. As x goes to 4, now that's going to be 1 over the square root of 4 plus the square root of 4. That's 1 over 2 plus 2 is 1/4. So in addition to ones like we did earlier where we can use, we can simplify a polynomial, when you have square roots, we can multiply by the conjugate of the part that has a square root in it, which will be the numerator. All right, notation for the derivative. The derivative was actually developed at pretty much the same time by two people in completely different places. Leibniz was working in Germany. Newton was working in England, working independently of one another. And because of that, what happens is that some people liked Newton's way of writing things. Some people liked Leibniz. And by the time anyone realized that they were doing the same thing, people were using both of these different ways of writing the derivative. So we're stuck with both. I kind of like Leibniz, although Newton's is faster to write. So for the function y equals f of x, each of the following denote the derivative. F prime of x, that's Newton's way of writing it, by the way, with just the little prime symbol. Or, more simply, since this f of x is equal to y, we could also write y prime. Leibniz preferred to write it this way, dy over dx. He called that the differential in y over the differential in x. To remind you that this comes from slope, the change in y over the change in x. He basically said that what was happening was it was a tiny change in y over a tiny change in x because the 2 points were really close together. So he no longer called it the difference in y over the difference in x. He called it the differential in y over the differential in x, which I think is kind of genius, actually. Another way to write that would be df dx. You almost never see this one. It just doesn't come up very often. The other way that you see this is now we think of this first part as being an operator on this. The derivative with respect to x of f of x. So this is the derivative with respect to x of f of x. So that's a slightly different way to write that. You will see this, the derivative with respect to x of f of x. So now this becomes an operator and not just a symbol. All right, so one of the things that we need to be able to do is estimate derivatives graphically. So here I have a graph of some function f, and then I have the graph of f prime, and I want to know at some points, and then I'm going to stitch those together, what does the graph of f prime look like? Well, remember that the derivative is the slope of the curve, or the slope of the tangent line, same thing, at a point on the function. So for example, at 4, right here, this is this low point. The tangent line would look like that. The slope of the curve is 0. So at 4, the derivative is 0. Right here, this looks like it's pretty close to the top. Actually, it looks a little bit past it, but maybe right there. Right in here, the slope is going to be 0. So at about 2, the slope is about 0. And again, on these problems, we're not going to get nutty about, well, it should have been, a tenth over or something. We're just getting the basic shape. Now, at this point, at x is 0 on the original, we can use a straight edge to get an approximation of the slope. And for you, it's going to be a little bit easier than it is for me. You could actually take, a ruler or, your driver's license or something and set it on here so that it looks like a tangent line. I'm going to have to kind of try and do it. Nope, that one's not good. Nope, that one's not good. That's better. Now, what I will do is I'll draw that long enough to where it goes to the next integer so that I can do a quick slope triangle. This went over 1. This went up approximately 1, 2 and a third, or 2 and a half, something like that. This is about 2 and a third. So 1, 2 and about a third is right there. The slope at that point is about 2 and a third. Doing the same thing at this next point, which is at x equals 1. Again, I want to draw this plenty long so that I can draw a slope triangle to my next integer value. So at 3, I've gone over 1. And then the question becomes, well, how much have I gone up? Well, I went up from here to here, a little more than 1. So at 1, I'm a little more than 1. At 3, again, I can draw in a tangent line. Looks about like that. I want to be sure to draw it long enough to where I can get it at least to 4, so I can draw in a slope triangle. over 1. And notice I'm going down this time. This goes over 1. This goes down about, let's see, it's at about 3, and it goes down to a little more than 0. So I'm going to say it's, 2.7. So at 3, I'm going to be at negative 2.7. And somewhere right about here. So what does this look like? Well, I'm going to connect this with a smooth curve. It looks like it gets a little bit steeper here, so I'm going to go a little bit further down than this 2.7. But then it's got to turn around and come back up. So it looks something like that. For this, what would I be checking? I would be checking that this at 0 is greater than the slope at 1, that the slopes at 2 and 4 are pretty close to 0, and that the slope at 3 is clearly negative. Those would be the things I'm looking for. If yours just didn't look perfectly like this, that would be fine. We can also estimate derivatives numerically. So take this example. Use the following table of values to estimate f of 3.2. So remember, f prime at 3.2 is the slope of the curve, or the slope of the tangent line at that point. Well, I don't know what happens exactly at 3.2, but I do know that on the interval from 3 to 4, I can find the slope. And that should give me an approximation, maybe not a great one, but an approximation for f prime of 3.2. So f prime at 3.2 is going to be approximately equal to f of 4 minus f at 3 over 4 minus 3. You might recognize that as the average rate of change. The average rate of change is between 3 and 4 is going to be some number. So the instantaneous rate of change at 3.2 should be somewhere nearby. So that's going to be 30 minus 26 over 4 minus 3. That's 4 over 1 is 4. And that's a very crude estimate, but it's the best we can do for this particular problem. Hope you guys have a great day, and please remember to study for your quiz tomorrow on sections 2.1 to 2.3. Have a good day.